Keep in mind that the ideal switch changes alternately from the off state to the on state instantly. Thus, we can sketch the voltage and current waveforms like this. However, practically, the power switch requires considerable time to change from the off state to the on state and vice versa. Thus, it creates a time delay before the power switch can conduct maximum current during the on state and blocks maximum voltage during the off state. Additionally, the product of current and voltage during the on state causes the power switch to produce the forward conduction power loss. Meanwhile, the product of current and voltage during the switching activity generates the switching power loss. As you know, power losses can affect negatively the operation of any power switches. Thus, to ensure reliability and efficiency, we need to use appropriate heat removal mechanisms such as heat sinks. Now, let's focus on how to calculate the power losses. In this topic, we will concentrate on the switching power losses only. As mentioned before, the power losses occur when a power switch changes from the off state to the on state and vice versa. According to the previous explanation, we can sketch the waveform of leakage current during the off state and the conducted current during the on state like this. Subsequently, we can sketch the waveform of voltage blocked by the power switch during the off state and voltage drop or on-state voltage during the on state as follows. In this graph, the x-axis is referring to the switching time in seconds, and we can see some delay before the power switch is entirely on or off. In between turn off and turn on, the delay is called the turn on time. It consists the current rise time and the voltage fall time. Instead, between turn on and turn off, the delay is called the turn off time. It consists the voltage rise time and the current fall time. Based on the area under both times, we can calculate the switching power loss using this following equation. You may refer to the note for a simple explanation and example on how to calculate the power loss. Nevertheless, based on the equation, we can see that the switching power loss is directly proportional to the frequency or the switching frequency of the power switch, where the switching frequency is equal to 1 over the switching time. Lastly, the next characteristic that will be discussed is the gate signal requirement. This characteristic only applicable to the controllable power switches. This slide shows several controllable power switches that require a gate signal or control signal to operate. Regarding the type of gate signals, thyristors and BJTs require current signals to turn on. Hence, they are known as current-controlled devices. Meanwhile, MOSFET and IGBTs need voltage signals to turn on, and they are called as voltage-controlled devices. For ideal power switches, it's stated that these devices only require a small current or voltage to initiate the on state. However, practically, these power switches require a substantial current or voltage to start the current conduction.